Good day. For those of you that don't know me, my name is Douglas Harder, and in this topic, we're going to discuss when two-dimensional vectors are equal, or vector equality. In this topic, we will review what a two-dimensional vector is. We will review what it means for two things to be equal. We will then define equality for two-dimensional vectors. We'll look at some examples and ask some questions. Now, remember first that a two-dimensional vector is ordered data. The first entry refers to one specific measurement, the second refers to a different measurement. For example, the two-dimensional vector negative 80.54 and 43.47 may represent the location of the University of Waterloo. That is, the first one indicates that it is at negative 80.54 degrees east, or equivalently 80.54 degrees west, and the second indicates that it is at 43.47 degrees north. Alternatively, these may represent voltages at two different nodes or locations within a circuit. Alternatively, yet again, they may represent money owed to you by Ali and Bailey, respectively. And in this case, here you would owe Ali $80.54. In all three cases, the vector 43.47 and negative 80.54 would represent something very different. Next, let's review the properties of equality. That is, what does it mean to say that x equals y? Well, here are the properties of equality. First of all, for anything being discussed, x must equal itself. X equals y if and only if y equals x. If x equals y and y equals z, then x must equal z. Now finally, here's an interesting one. If x equals y, then any relevant question about x will have the same answer when that same question is asked about y. Okay, so given these properties of equality, let's actually look at a definition of equality for two vectors. Let's say we have two two-dimensional vectors u and v. We will say that u equals v if and only if the first two entries are equal and simultaneously the second two entries are equal. So let's look at some examples. The vector 0.3, 0.9 does indeed equal itself. If I swap the entries, these two vectors are not equal. Why? Because 0.3, the first entry of the vector on the left, does not equal the value 0.9, which is the first entry of the vector on the right. On the other hand, vectors store numeric data. So whether or not a vector contains 0.3 or 3/10 or 2.5 or 5/2, both of those are numerically the same value. And so those two vectors would be considered to be equal. Negating one of the entries of a vector, unless you're negating 0, will produce a vector that is different, because 1.7 does not equal negative 1.7. And similarly, just because one of the entries of a vector are equal, it doesn't mean the two vectors are equal. Both entries of the vector must be equal. Okay, now let's take a look at these two vectors. Are these vectors equal? Well, not really. They're not. The last few digits are slightly different, but most of the digits are the same. So are they almost equal? Similarly, let's take a look at these two vectors. Are they equal? Well, once again, we notice that, well, the first four digits are equal, the rest of the digits are unequal. Now, suppose this was a measurement of how tall an object was that was in meters. Are those almost equal? Well, under most circumstances, they probably are. So, while these are not technically equal, they may, under engineering conditions, be sufficiently equal for the question at hand. So we will discuss this concept later. But technically, both pairs of these vectors are indeed not equal to each other. In the two-dimensional plane, two vectors are equal if and only if they both represent the same point on the plane. So, in summary, in this topic, we've introduced equality between two-dimensional vectors. We've described equality, and we've stated that two-dimensional vectors are equal if and only if both entries are equal. We looked at some examples, and then we looked at some examples of vectors that are almost, but not exactly equal. Here are some references, acknowledgements, the colophon, and a disclaimer. Cheers!